Hello, my name is Ethan Fahnestock, and this summer I worked on the problem of motion planning for parts assembly with environmental uncertainty under the mentorship of PhD student Shivam Vats and Professor Maxim Likachev in the Search-Based Planning Lab. The focus of this work is parts assembly. Defined broadly, parts assembly is the task of arranging objects within relative positions of one another, in a way that usually involves contact between those objects. Robotic parts assembly may make you think of automobile manufacturing, like the graphic this slide depicts. Robots in these settings usually rely on highly structured environments. The robots execute hard-coded sequences to complete their contact-rich tasks, such as assembling the frame of a vehicle. Assembly tasks are common outside of structured factory environments. For example, consider the task of screwing on a lid to a jar, as shown on the left. This household assembly task illustrates the requirement for tight tolerances, as if the lid was slightly off-center, one could not complete the task without repositioning it. This example also illustrates the contact-rich nature of the assembly task, as completing it necessarily involves contact between the jar and the lid. To approach these tasks in less structured environments, robots need to be more flexible, as pre-programmed sequences will be fragile. Due to the tight tolerances, any displacements in an object's position from where it is expected to be is likely to cause a pre-programmed sequence to fail. Uncertainty inherited through perception of the robot's environment, an example of which can be seen in the shifting bounding box of the drill on the right, is usually significant enough to cause this failure mode. As opposed to hard-coded sequences, robots can plan actions adapted to their current environment. However, traditional motion planners avoid all contact, which is not feasible for assembly tasks. And if while executing a path, contact occurs, it can damage the manipulator or the environment. These planners can be modified to generate solutions that can safely handle contact, for example, by executing generated paths with impedance-based control, which better enables contact by adapting to external forces. In this work, we aim to create a planner that can utilize contact to reduce environmental uncertainty, enabling completion of assembly tasks outside of highly structured environments. Contact-rich manipulation has been approached in a variety of ways. One, here on the left, frames the problem as a Markov decision process, considering uncertainty in the robot's action, but not in the robot's environment. Two, center, frames the problem as a partially observable Markov decision process, using a particle filter to represent environmental uncertainty. Both of these approaches also utilize impedance-based control and physics-based simulation, but neither use graph-based search. In this respect, our work is most similar to 3, right, which uses multi-heuristic A* and a physics-based simulator for parts assembly. This work accounts for environmental uncertainty by planning in belief space. Our work differs in our use of impedance-based control. We formalize the problem of motion planning for parts assembly as the search for a sequence of actions A that, when executed from an initial state S, places one object within a goal pose with respect to another, within a set tolerance. We also make the following assumptions. In order to perform the physics-based simulation, we assume knowledge of object geometries and physical properties, as well as those for the manipulator. We also assume good state feedback from the manipulator. Our approach has 3 key components. First, we discretize the robot's configuration space with a graph. We employ state lattice with controllers, or SLC, to build this graph, instead of traditional motion primitives, which generate a successor to a parent state in a fixed way. SLC uses controllers, or actions, as motion primitives. A controller is made up of a relative transform, which is applied to the robot's current state, and a termination condition which ends the action, returning the end state as a successor. Moving to the second key component, we use physics-based simulation to evaluate these controllers. This allows for contact to influence actions during planning, but comes at a high computational cost. To mitigate this, we utilize GPU-accelerated physics simulation to parallelize the evaluation of controllers. Finally, we use operational space impedance control as the base of our controllers. With this control method, an attractor is set in Cartesian space, which pulls the end effector towards it until an equilibrium position is reached, where external forces such as contact balance out force from the attractor. This allows for safer handling of collisions during execution. Evaluating the proposed method's performance with environmental uncertainty is a work in progress, but we have demonstrated the ability of our method to solve a board and slot assembly task without environmental uncertainty, as can be seen in the video on the right. The planning and motion primitive details can be seen on the left, as well as an image depicting the board and slot assembly task, which consists of inserting a board, shown in red, into the slot, shown in blue. As previously mentioned, work is in progress to evaluate the solution found by the proposed method, while varying levels of Gaussian noise are added to the slot position. A baseline of a planner using metric primitives and no physics-based simulation will be used to evaluate if the proposed method is more robust to environmental uncertainty without explicitly considering it during planning. From here, methods will be explored to motivate the planner to select actions that produce small variances in successor states when evaluated across environments with sampled slot positions. Potential future work may also involve using the paths generated with this approach to seed reinforcement learning approaches for assembly tasks. These are my references used throughout my presentation. I would like to thank all of the RISC program sponsors that made the summer opportunity possible. I would also like to thank Professor John Dolan and Rachel Burson for organizing the program and adapting it to its remote form this summer, my mentors for their advice and feedback, and the RISC cohort for their support. Thank you for your time.